Okay, so in this review, we're going to talk about calculating growth rate, what growth rate means, a couple different ways that we've talked about how to calculate it, and then how to use it to determine how long it would take for a population to double in size, called doubling time. So first of all, it's really important to remember that growth rate is simply just a rate. And whenever you have a rate, it's some change in variable over your change in time. So growth rate is your change in population size over your change in time. In the simplest way, that's what all of these questions are. How is your population changing compared to how time is changing? So if you have a population that increased by 20,000, you can think of your change, if I can get this right, your change in population, which is dn, over your change in time, which is dt, and that is equal to your growth rate, which we say is r. So here our change in population, or our dn, is 20,000, sorry my handwriting, and our change in time, or our dt, is 3. So if we do 20,000 individuals, we want to keep those units. Units are really, really, really important. If it's the FRQ and you get all the way to the end and you don't have units, you don't get points. It hurts. So 20,000 individuals divided by 3 years is equal to our R. And if we do that math out, it equals 6,666.67 individuals per year. And of course we would want, you can't have 0.67 of an individual, so round. Okay, awesome. Let's clear that and go to the next. So I can tell you how the population changed. We increased our population by 20,000, or I can tell you that we had this amount of change, calculate the growth rate. So here we have a population of 40,000 experiences 340 births. So we remember this as births plus immigrants minus deaths plus emigrants. And emigrants are the number of individuals that leave your population, and immigrants are the number of individuals that enter your population, not from birth or from death, just from migration. So they can either migrate in, and that's called immigrant, or they can migrate out. Ooh, that should say emigrant, migrating out. Over our total population size, which is n, this will also give you r. Okay, so births is 340, immigrants is 60, deaths is 500, and emigrants is 70. And for this, it's really important to remember your rules of order, that you want to calculate what's in the parentheses first, and you have to keep that PEMDAS, keep your order of operations correct. So births is 340, plus our emigrants, which is 60, minus our deaths, which is 500, plus our immigrants, which is 70. So here, over our total population, which is 140,000, and that is equal to our annual percentage growth rate. So this is, if we simplify it, we do what's in the parentheses first, so 400 minus 570 over 140,000. And now we have to do our subtraction first. So 400 minus 570 is negative 170 divided by 140,000. And that is negative 0.0012. So we're going to be decreasing by 0.0012. That's our annual percentage growth rate. It's actually decreasing in rate. All right, cool. Let's keep going. So our populations can grow exponentially or logistically. And we're still using that same equation, we're just manipulating it a little bit. So exponential growth is growth without limit. So we're just increasing in population size with no end in sight. And generally we think about having this type of growth where you either have an individual colonizing a new area where there's so many new resources, there's no competitors available, so you're just increasing in size and nothing's holding you back. Or all of a sudden you maybe have a new adaptation, you're able to tap into a resource that wasn't available or accessible to you before it. So again, you're having a big growth in population. There are no real factors keeping that population in check. Here we're going to talk a little bit about density-independent factors. Density-independent factors are usually tied into exponential growth. In exponential growth, you have these big booms followed by bust periods. And what makes that bust happen are these density-independent factors. And density-independent factors, regardless of how dense that population is, the factor itself does not change intensity. So it's, of course, whenever you have more individuals are going to die from an event. However, the impact of the event, the intensity of that event doesn't change. So think about a hurricane. Regardless of whether there's a big population or a small population, a hurricane with a Category 5 is still going to come and hit the shore with the same amount of intensity. So natural disasters generally are a really great example of density-independent factors. So let's do an example of exponential growth. Again, our equation here is change in population size, dn. This is change in population size divided by our change in time, it's a rate, equals our maximum growth rate times our population size. So if we have a current population of 450, that's going to be our n. It increases in size exponentially. That's my hint that we're going to use the exponential equation. So let's underline it because that's important. Over 10 years, so that's our dt, that's our change in population size. And added 100 new individuals, that's our change in population size. And I ask you to calculate the maximum growth rate, and that's what we're looking for. So dn is 100 over dt, which is 10, equals r times 450. So if we simplify this down, we remember order of operations is really important. 100 divided by 10 is 10 equals r times 450. And if we divide both sides by 450, we get our r, which is 0.022. Awesome. I can give you any of these variables, or I can leave out any of these variables, and I expect that you'll be able to plug it in. The hardest part about these equations and using them is figuring out what I've given you. So as long as you're able to remember that dn is your change in population size, dt is your change in time, r is your maximum growth rate, and n is your current population size, you can do anything. All right, let's do logistic growth next. So logistic growth is when there is a you're not expanding unlimited amount, you're not increasing, you're increasing up to and around this carrying capacity. These graphs make me a little bit sad because once you hit your carrying capacity, it's not like, I hit my carrying capacity, that's it. You end up with these little fluctuations. So generally you'll see some graphs where they'll show that fluctuation. That's a lot more realistic to what happens. You don't hit your carrying capacity and stay there. You fluctuate around it. This is biology. So, okay, so resources are limited, which keeps your population in check. Or there's a lot of competition or a lot of predation. Something is keeping your population at this carrying capacity. So you can increase in size seemingly exponentially at early growth until you reach this carrying capacity, until one of your density-dependent factors start keeping your population in check. So density-dependent factors increase their intensity with increasing density. So think about something like competition. If there's maybe one or two individuals and they're using the same resource and there's plenty of resource, they're not really competing. But as you increase that density and that resource is fixed, you have a limited amount of resource, now competition becomes more and more intense. That's a beautiful example of density dependency, factor that's density dependent, because it becomes more intense as you increase your density. Predation also becomes more intense as you increase your density. Disease becomes more intense as you increase your density. The impact of your factor becomes more intense with an increasing density. Okay, so let's do a practice. Let's find that R. So our equation's a little different now. dN and dt are still the same. dN is still our change in population size. dt is our change in time. R is still our growth rate. N is our current population size. K minus N, our carrying capacity minus our population, divided by K, our carrying capacity. And now it's going to be really important to remember our order of operations and to not move outside of our order of operations. So you want to do what's the inside most first. So when it comes time to calculating, this K minus N is going to happen first because of our order of operations. It's the innermost parentheses. We have to do that first. If you start doing other things first, your answer is going to be wrong, and that's going to be sad, especially if you get the whole equation wrong and then your order of operations is wrong. Okay, so a population of 76,000. This is our N. Increased in the population by 6,000. So that is our change in population size, or dN. Over the course of 10 years, that's our change in time. So that's dt. And has a carrying capacity of 90,000. So that's our K. And I'm asking for our maximum growth rate, which is R. So dN is 6,000 over our change in time, which is 10 years, is equal to R times N, which is 6,000. Oh, I'm sorry. It's not 6,000, it's 76,000. And remember to keep those units. 76,000 individuals. I'm gonna do 76,000, and then our carrying capacity is 90,000 minus our population, which is 76,000, divided by our carrying capacity, which is 90,000. Okay, so we want to do the innermost portion first, which is this one. We're going to do K minus N. So K minus N, 90,000 minus 76,000 is 14,000. So let's just replace that with 14,000. And then we can do 14,000 divided by 90,000, and we get 0.0156. 0.01556, and then we can multiply that by our population, which is 76,000, and then we get 11,822.22. And now let's go look at our other side, our dN over dt, which is 6,000 divided by 10, which is 600. So let's replace that. And now we can divide our final step, 11,822.22, from both sides. and then we'll get our R. And I got 0.0508. All right, so now I've got that. What do I want to do with it? Maybe that's it. Maybe I just asked you to calculate the growth rate. Maybe I asked you to compare it to another growth rate or what you would expect to see at a different point in this curve. Awesome. But what we're going to do next is, with any of these R's, is I can ask you to calculate how long it would take for the population to double. So there's this cool equation called the rule of 70, and basically it means the number of years it would take for a population to double is equal to 70 divided by the annual percentage growth rate divided by R. So if you have an annual percentage growth rate of 0.3, and the annual percentage growth rate, the one that one is the one, it's the birth plus immigrants minus deaths plus emigrants over total population size. That's annual percentage growth rate. So 70 over 0.3 would be the number of years to double. So the number of years to double is 70 over 0.3. So for this population that's growing at a rate of 0.3, it would take about 233.3 years to double. So if we came back in 233.33 years, we could expect that population to be doubled in size. So if it was 1,000 now, in 233.3 years, we'd expect it to be double that size, 2,000. Okay, so we can also do it the other way. If it takes a population 100 years to double, what is the annual percentage growth rate? So then instead of giving you the annual growth rate, I'm actually giving you this, the number of years to double. So 100 equals 70 over R. So we can do 100R equals 70, and then we divide 70 by 100, and we get R equals 0.7. That's it, folks.